Okay, good morning, everyone. So last time we had started talking about the coherent states of the harmonic oscillator. Okay, and we're just sort of picking these out of thin air. We will show later in this lecture that they obey the properties that they're classical-like, but for right now, we're just saying that we're looking for eigenstates of the lowering operator. So look for eigenstates of the operator that we've been calling A, which means that A, acting on the states we're looking for, gives back, which we're calling alpha, gives back the complex number alpha times the state. And the reason it's complex, or it can be complex, is because the operator A is not Hermitian. And so what we'd found last time is we'd found that up to normalization, meaning up to a constant multiplying the state, we'd found that the state alpha is equal to some overall constant C0 times an infinite sum, n equals 0 to infinity, times the complex number alpha to the nth power over the square root of n factorial times the energy eigenstate n. So these are stationary states whose energies we have worked out. Okay, so now we want to find what is the constant C0. And to do that, we just require that our state alpha has unit norm, which means alpha alpha is equal to 1. And so we just plug that in. We're saying we want 1 to equal, first of all, the bra of this alpha is C0 star times a sum n equals 0 to infinity. N, we have to remember to complex conjugate alpha. Okay, so there I've written the bra for alpha, and now I want to write the ket for alpha again. And when I do that, I should be careful that when I write the infinite sum, I use a different symbol for this n right here, because I've already used up n here. So I better call this a different name so I don't get confused between the two infinite sums. So I'm going to call it sum m equals 0 to infinity, alpha to the m over the square root of m factorial times m. Because I'm doing a sum twice, I don't want to get confused between n and m. Okay? And so now I can combine things a little bit. I'm going to take C0, C0 star and write that as magnitude of C0 squared. I'm going to write my sums on the outside. So n equals 0 to infinity, sum m equals 0 to infinity. And then I'm going to pull out the remaining constants, which are alpha star to the n, alpha to the m, over square root of n factorial m factorial. And then I have nm. Okay, because there are no operators left in this equation, I can just pull out all the constants. And then the inner product of n with m is, by definition, because they're defined to be orthonormal, just delta nm. In other words, it's only non-zero when m equals n. And so when we do, let's say, the m sum here, there will only be one term that contributes, and that's the term that has m equals to n. So we can write this as a single sum. Well, let me just write here. So in the m sum, only the term with m equals n survives. Okay, and so I can write this as magnitude of C0 squared. C0 is what we're trying to find here. Sum n equals 0 to infinity of the magnitude of alpha to the 2n divided by n factorial. I've just set m equals n. And now the nice thing is this part right here is an exponential. By the definition of the series for the exponential, this is C0 squared times e to the magnitude of alpha squared. Okay, so now we can figure out what C0 should be. Namely, C0 up to a phase, there's always an arbitrary phase in these things that you can't determine because it's not observable. This is the exponential of minus alpha squared in magnitude divided by 2 in the exponential. Okay, and so what we've learned, if we summarize this, is that the state alpha that's an eigenstate of the annihilation operator is e to the minus magnitude alpha squared over 2 times an infinite sum from n equals 0 to infinity of alpha to the n over the square root of n factorial acting on the energy eigenstate n. Okay, and so that is our state. It's defined to be that it satisfies A alpha equals alpha times alpha. It satisfies alpha the bra times A dagger equals alpha star times the bra alpha. And it satisfies the normalization condition, alpha alpha is equal to 1. All right. There's an alternative way to write this. So for an alternative form, which is sometimes more useful, we're just going to take the state n and rewrite it in terms of the ground state with a bunch of creation operators acting on it. So recall that the state n appearing in that infinite sum, we can write as a dagger to the nth power over square root of n factorial, acting on the ground state. Okay, so if we just plug that in, then we get alpha equals e to the minus magnitude alpha squared over 2. And now we can combine the nth power of a dagger with the nth power of alpha. Okay, and so this is a dagger, or let me write it this way, alpha a dagger to the nth power. We have, from here, we have a 1 over square root of n factorial, and we have a 1 over square root of n factorial from there, which neatly combine. And so this is just over n factorial, all of that acting on the ground state. And the nice thing about writing it this way is, again, the infinite sum here, because it's something to the nth power divided by n factorial, that just combines into an exponential. And so this is, in fact, the exponential of alpha a dagger. Okay, so this is an operator as opposed to the first exponential, which is a number. So that's why I could, of course, combine those two exponentials, but let me keep them separate because one of them is a number and one of them is an operator. But it looks like this, alpha a dagger, all acting on the ground state. Okay, so that's just another way of writing our state alpha. All right, so now the strategy is we're going to examine the properties of this state and show that it really does behave something like a classical state or a semi-classical state. And the first thing we want to look at is things having to do with the energy of this state. So I can ask the question, given the state alpha, what are the possible results of an energy measurement? Once we figure out the possible results, we'll figure out their probabilities. So the answer to that is just that if we look at, for example, this version of it, we see that it's a linear combination of every possible different state, every possible different energy eigenstate n, because we're summing over them all. Okay, and so that means that all energies are possible results. And the energies eigenvalues are h bar omega times n plus 1/2. So all of those can occur and will occur. And then we can apply the postulates of quantum mechanics to find their probabilities. So with probabilities, okay, so recall from the postulates of quantum mechanics, the probability of getting the result E sub n is equal to a sum over degeneracy labels rho sub E sub n times the state E sub n rho sub E sub n alpha, if we're in the state alpha, squared. This is a degeneracy label. And this is a very general expression, which in the present case is going to simplify because it doesn't occur here, because there are no degeneracies. So I'm writing it that way to be completely general, but it doesn't occur here. In fact, the states that do occur here are just the states n. Okay, so this probability is the square of the inner product of n with alpha. Okay, and now if we go back up to this master equation, we're taking the inner product of that with n. And so all we do is we pick out this coefficient of the ket n in the expression, multiplied by the overall coefficient. Okay, so this probability is going to equal, or the matrix element is going to equal the square of e to the minus alpha magnitude squared over 2, alpha to the n over the square root of n factorial. So all of that squared. Okay, or we can rewrite this as e to the minus alpha squared times the magnitude of alpha to the 2n, because when I do this, I'm taking this multiplied by its complex conjugate. And then in the denominator, we have 1 over n factorial. Okay, so if you ask somebody who is an expert on statistics what this sort of probability distribution is called, they will say, aha, this is, in words, this is a Poisson distribution. And in fact, they'll even tell you that this is a Poisson distribution with mean as an average equal to the magnitude of alpha. Okay, and so in particular, even though the state depends on the phase of alpha, this distribution of probabilities does not. So it doesn't depend on the phase of the complex number alpha, which it could have, but it so happens that it doesn't. All right, so let's look at some properties of this distribution of possible probabilities and how they depend on n. So it's always a good thing to first look at extreme cases. So first of all, what happens for small n? Okay, so for small n, what's going to happen is that the exponential of e to the minus alpha squared here is going to win. And so this is going to be the exponential of minus a very large number. And so that's going to go to 0. Okay, so e to the minus alpha squared wins. And so this probability distribution will go to 0. On the other hand, for large n, then what always wins for large n is n factorial beats any power. And so this denominator is going to get very large, which means, again, it's going to be very small. So in this case, the 1 over n factorial wins. Okay, and so this goes to 0. And now we can ask, okay, what happens for n in the middle? And so one thing to notice from this distribution is that if I look at the probability of getting E sub n, that's equal to alpha squared in magnitude divided by n times the probability of getting one smaller energy, En minus 1. So what does that mean? That means as n increases, the probability will increase as long as this prefactor here is greater than 1. But eventually, n will start to win in the denominator, and it will start decreasing again. Okay, so the probability, so as n increases, the probability will increase until n becomes larger than the magnitude of alpha squared. Okay, and then it will decrease from there on. So from those pieces of information, we can draw a graph of what we expect the probability distribution to look like as a function of n. Remember, n has to be an integer though, and this is the probability of E sub n. And so what we've said is the point magnitude alpha squared is special. And then if we just draw points, it's very small out here, and it's very small here, and here it's reaching a peak. So naively, I'm drawing a dot for each point in n. It's going to look something like that. Okay, and then if I want, I can connect the dots. And so that's naively the shape of the energy probability distribution. So as we'll see, though, there's something qualitatively not right about the figure that I've just drawn, but we'll compute that in just a minute. Okay, questions so far? All right, so we have the probability distribution, and so the next thing we can do is ask for the expectation value. So just from the graph, we can pick out where the expectation value ought to be. It should be about here. The expectation value of the energy should correspond to n's that are close to this. But let's just do it and see what happens. Okay, so expectation value for the Hamiltonian. And so the definition of that is we take our state, we sandwich the Hamiltonian in between. Okay, and we know in the harmonic oscillator case how to write the Hamiltonian nicely in terms of creation and annihilation operators. Namely, it's h bar omega a dagger a plus a half. Okay, and the nice thing about this is we know how this A acts on alpha, namely it just gives you a factor of alpha. And we know how A dagger acts to the left on the bra alpha, that just gives an alpha star. So we can write this as equals, let's pull out the factor of h bar omega, and then there's alpha, alpha star from the A dagger. Okay, and then there's alpha A from the A acting on the alpha. And then there's the 1/2, which is just 1/2, because there's no operators in there. And so we can rewrite this as h bar omega times the magnitude of alpha squared plus 1/2. Okay, so from the figure here, we would have guessed it was about h bar omega times the value of n, which is approximately alpha squared. And we see that was almost right. There was just an extra plus 1/2 there. But alpha is going to turn out to be alpha magnitude is going to turn out to be a large number. And so this is a very small correction. Okay, and so again, this magnitude of alpha squared is going to be the most probable value that you'll get for n if you were to measure it. All right, so that's the expectation value, and then there's the uncertainty in n, which is basically, roughly speaking, it's the width of this distribution. But let's figure out what it is just from the formulas. So energy uncertainty. So we know for the uncertainty, the thing we need to calculate is the expectation value of the operator squared, which in this case is the Hamiltonian squared. Okay, and so again, there's going to be an h bar omega for each Hamiltonian, but there's two of them. And then what we need to write is alpha, we have the square of the operator A dagger A plus 1/2, sandwiched in between the bra and the ket for alpha. Oops, I forgot to square this. That's very important. So now we can write that all out, expand that out as h bar omega squared, and then there's alpha A dagger A dagger A, alpha. Okay, and then there's going to be two terms, but multiplied by 1/2 with just A dagger A. So that's going to be alpha A dagger A, alpha. And then there's finally going to be this term squared, which is going to be plus 1/4 alpha alpha, which again is just 1. Oops. So let's work out what this gives us. So there's an h bar omega quantity squared. Okay, and then the great thing about alpha being an eigenstate of A and alpha the bra being an eigenstate of A dagger is that we know all we have to do is replace each A by alpha, because it will be acting on a state alpha, and each A dagger by alpha star. Okay, and so for example, in the first term, we can rewrite that as alpha star alpha. I've eliminated one of the A and A daggers, and then I've got A dagger. And now I can almost replace this A dagger by an alpha star, except the problem is A alpha is an eigenstate of A, not A dagger. So I have to do the normal ordering trick, which is to take the A dagger and replace it by A dagger A plus 1. That comes from the commutation relation. Okay, and so when I do that, then I can replace A dagger A by alpha star alpha plus 1. Okay, and then let's do the next term. The term here with from there is just equal to alpha star alpha. There are no ordering problems. Okay, plus 1/4. And so when I add all that up, we get h bar omega squared times the magnitude of alpha to the 4th power, plus there are going to be two terms with magnitude of alpha squared. One of them's here. The other one comes from this plus 1. And so that's plus 2 alpha magnitude squared plus 1/4. Okay, so now we have the expectation value of h, and we have the expectation value of h squared. And so right into the definition of uncertainty, we get the uncertainty in the Hamiltonian, otherwise known as the energy uncertainty in this state. Okay, by definition, that's the square root of the expectation value of a squared minus the expectation value of h squared. Okay, and we just plug in. We've got, first of all, everything's proportional to h bar omega. We can just tell that from dimensional analysis. And then we've got square root of alpha to the 4th plus 2 alpha squared plus 1/4 minus the square of alpha squared plus 1/2 squared, which I can write as h bar omega square root of alpha to the 4th plus 2 alpha squared plus 1/4. I'm going to multiply the rest of this out as alpha to the 4th plus 1. Oops, but it's got a minus sign in front. So minus 1 alpha minus 1/4. And then the nice thing is that cancels with that. The 1/4s cancel. And these two almost cancel, but one of them has a 2 in front of it. Okay, and so the whole thing is just h bar omega times alpha.
So that second term on the right, should that be alpha squared then, right?
Yes, very good, thank you.
Okay. Thanks.
Okay. So now we can compare the uncertainty in h to its expectation value. And that's approximately, well, it's equal to, the h bar omegas cancel. And so there's an alpha over alpha squared plus 1/2, which is approximately just 1 over alpha if alpha is large in magnitude. So this is going to be very, very small. Okay, so in fact, let's say we're talking about a state with a very large amount of energy. If we go back to here, what we find is that the n that we're talking about, I'm back up here, the n that we're talking about is proportional to alpha squared, or is approximately equal to alpha squared. And so if we're talking about a macroscopic amount of energy, very large compared to 1 quantum, then n is approximately alpha squared, or alpha is approximately equal to n. Okay, and so for our numerical example last time, this is in fact roughly 10 to the minus 16 for our numerical example. A very small number. Okay, so that means that when I drew the qualitative picture of the probability distribution in energy, I was distorting things quite a bit, and it should have looked more like the following. as a function of n, if I look at what's the probability distribution of getting an energy n, okay, it's peaked at around 10 to the 32 for a numerical example, but it's an extremely narrow distribution because the uncertainty is this tiny number. So in fact, I should have graphed it more like the following. Some extraordinarily sharply peaked, I'm even showing the width too much, right? It's very, very sharply peaked about that one energy. And so that's one sense in which this is a quasi-classical state. So quasi-classical means sharply peaked. But that's not the only aspect, as we will see, that's saying it's quasi-classical. But it's saying if you measure the energy, you're extraordinarily likely to get one particular value and not any other particular value. All right, so that's for energy, and now we can do the same thing for other observables that we could measure, namely position and momentum. So for example, we can look at what's the expectation value of position. By definition, it's that. And now the nice thing to do is to plug in x in terms of creation and annihilation operators. So that looks like this. So there's an A plus A dagger multiplied by a length scale. And again, the nice thing about alpha being a eigenstate of A is we can just turn A plus A dagger into alpha plus alpha star. The reason I can turn it into alpha star is because I'm acting backwards on that alpha. Okay, and another way of writing that, depending on what you're doing, one of these might be more convenient than the other, but this is going to be square root of 2 h bar over m omega times the real part of the complex number alpha. Okay, so that's the expectation value of x. And if we want the uncertainty, we're also going to want expectation value of x squared. Now there are going to be two factors of h bar over 2 omega, square rooted. So that just gives that factor. And then there's alpha a plus a dagger squared alpha. So now we have to multiply out this a plus a dagger. There's one term with a squared. There's one term with a dagger. Another term with a dagger a. And another term with a dagger squared. And we want the strategy again is normal order. So we're going to take the a dagger and replace it by a dagger a plus 1. And then once you do that, every a can turn into an alpha and every a dagger can turn into an alpha star. And so this equals alpha squared plus 2 alpha star alpha plus alpha star squared. And then there's the leftover plus 1, which comes from this. Okay, and so I can write this as alpha plus alpha star squared plus 1, all multiplied by h bar over 2m omega. Okay, and so now we're ready to compute the uncertainty in the position. Delta x is square root of x squared minus expectation value of x squared is square root of h bar over 2m omega. And we just plug in what we've got so far, alpha plus alpha star squared plus 1 minus alpha plus alpha star, quantity squared. Okay, that's coming from this equation. Okay, and now that just cancels that, which is nice. And so delta x, the uncertainty in x, is just square root of h bar over 2m omega, which has a couple of amusing properties. One is that the dependence on alpha has completely canceled out. So it could have, but it doesn't depend on alpha. And not only does it not depend on alpha, but if you remember what the uncertainty in x was for the ground state, it was the same exact expression. So this is the same as for the ground state of the harmonic oscillator, even though the state alpha and the ground state are very different states. Okay, so that's computing the uncertainty in x. And similarly, you can compute the uncertainty in the momentum. Okay, and that's alpha. Well, first we'll do of course, the expectation value. And you get that that's equal to the square root of 2m h bar omega times the imaginary part of alpha. Okay, and the uncertainty in the momentum turns out to be the square root of m h bar omega over 2. And so the same comments apply to this. It could have depended on alpha, but it turned out not to. And it's the same exact thing as for the ground state. And so in particular, now you can look at the uncertainty principle for this state, and we find somewhat surprisingly, at least to me, that the product of uncertainty and position and momentum is just h bar over 2. And we had a theorem that said that was the smallest thing it could possibly be for any state. It's true for the ground state, but it's also true for this coherent state. So this is as small as it could possibly be. All right, so what is that saying? That's saying that even though this is for general alpha, this is a macroscopic state, the uncertainty in momentum and the uncertainty in position, their product is the same as if this were some very microscopic state with zero quanta, energy quanta. So now what we can do is say, okay, that's for the state at some fixed time, but now let's see what happens when time evolves. So far, have worked with the state alpha at some fixed time, let's say t equals 0. And we can say, how does the state, first of all, how does it depend on time? And then once we've worked out how the state depends on time, we can think about things like how do the expectation values depend on time. Okay, so we know that if the Hamiltonian doesn't depend on time, which it doesn't for a harmonic oscillator, we can write this as e to the minus I Hamiltonian t over h bar, acting on the state psi 0. Okay, there's no need for a Dyson series because the Hamiltonian doesn't depend on time. And this we're assuming is just the state alpha. So this is equal to e to the minus I ht over h bar. I'm going to write down what the state alpha was. It was sum n equals 0 to infinity of alpha to the nth power over the square root of n factorial times n. And then there was also this factor of e to the minus alpha squared over 2. Okay, now the nice thing about doing that is then, since I'm acting on energy eigenstates, my H I can just turn into the corresponding energy and it becomes a number. This is a general strategy for dealing with these things. So I can write this as infinite sum alpha to the n over the square root of n factorial. And then my exponential, the first exponential turns into e to the minus I omega n plus 1/2 times t, the h bars cancel, times n, and then I've got my other exponential, like so. And now I'm going to rewrite this slightly. First of all, I'm going to pull out the e to the minus I omega t over 2 factor, but I'm going to leave the other exponential, the other part of the exponential in there and combine it with my alpha. So this looks like alpha e to the minus I omega t to the nth power, acting on n, e to the minus magnitude alpha squared over 2. Okay, so what was the purpose of that? The purpose of that is that now I recognize all of this stuff as having or all of this including that, as having the exact same form as a coherent state. It's just that it has a different value of alpha now. Okay, and so in fact it has e to the minus I omega t over 2 times the coherent state with alpha e to the minus I omega t. Okay, so what does that mean? That means the coherent state turns into another coherent state. It's not the same coherent state. This first factor in front is just a global phase. So you can ignore that if you want. It doesn't affect anything. But this phase inside is not something you can ignore. So this is an important phase. And you can say, how do I know that phase is important? And one way to think about it is go back to the previous expression where there's an e to the minus I omega t, but there's a different power of it, namely n, acting on each of the stationary states. So that means there will be interference effects between different stationary states that contribute to the sum that have different phases in them. So that's why this is an important phase that you can't just ignore, whereas this global phase that multiplies the whole thing that we pulled out, notice it didn't depend on n here, is something that doesn't affect probabilities or expectation values or anything like that. Okay, so what have we learned? We've learned the time evolution takes a coherent state into another coherent state with a different phase in the definition of alpha. Okay, and so alpha is being replaced by itself times e to the minus omega t. And so let's say we started with alpha equals its magnitude times some other phase at the initial time at time t equals 0. Okay, so this is by definition a real number because it's a magnitude. Okay, and so now because we've worked out what the expectation value of x is for any coherent state, we know that the time dependence of the expectation value of x is square root of 2 h bar over m omega, real part of magnitude of alpha e to the minus I times omega t plus the initial phase. And similarly, the expectation value of the momentum operator as a function of time is square root of 2 m h bar omega times the imaginary part, of the initial magnitude alpha times a phase. In fact, it's the same phase as for the position. But now we're taking the imaginary part rather than the real part. Okay, now we can go ahead and take those real and imaginary parts. So again, these equations just came from plugging into, where is it back up here, into this equation for expectation value of x, and this equation for the expectation value of p. It's just that now we're plugging in the time dependence of alpha in each of those equations. Okay, so working out what those real and imaginary parts are, we get the expectation value of x as a function of time is square root of 2 h bar over m omega. The magnitude of alpha is a real number, so we can pull it out of the real part. And then the e to the minus I omega t, blah, 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 just gives a cosine of omega t plus phi 0, which we can rewrite as just saying, let's call all of this stuff in front, x0. We can rewrite this as x0 cosine omega t plus phi 0, which is nothing other than the classical dependence of position on time. Same thing for momentum, except it's got a different factor in front, namely negative square root of 2 m h bar omega, but it's got an alpha and it's got a sine, omega t plus phi 0, which is minus m omega. And once I've decided what to call x0, namely this stuff, then this factor is going to be minus m omega x0 times sine omega t plus phi 0. And that's nothing other than the classical trajectory of the momentum. Okay, so let's summarize what we've learned about our state alpha. Okay, so one thing is about energy. We've learned that the expectation value of the energy is equal to h bar omega times the magnitude of alpha squared plus 1/2. And by the way, notice the magnitude of alpha didn't change. Alpha just got changed by a phase when we evolved in time. So this is a constant. Even though the state is evolving in time, the expectation value of energy isn't changing. And its uncertainty is h bar omega times the magnitude of alpha. The expectation value of position is nothing other than the classical value. And its uncertainty is very small. The smallest it could possibly, oops, that's not an h. That should be an x. Okay, and the expectation value of momentum is the classical value of the momentum. And it has the smallest uncertainty it could possibly have. And none of these things change in time. So this thing is sharply peaked in energy and position and momentum, and the uncertainties are constant. So it doesn't spread out. So you may remember when we talked about the Gaussian wave function for a free particle, if we started it out sort of sharply peaked, then the peakedness of it would decrease. It sort of spreads out in time. But a harmonic oscillator potential is sort of magical in that you can create this coherent state and it just sort of persists evolving classically, but without its uncertainties changing, right? And the amplitude for the oscillation, which we can just define to be x0, is square root of 2 h bar over m omega times alpha. So if you have a macroscopic harmonic oscillator in your lab and you want to figure out what's the coherent state alpha for it, you can just measure its amplitude with your meter stick, plug in h bar and m and omega, and figure out what the alpha is for the corresponding quantum state that most closely resembles it. Okay, and so if I were to make a graph here as a function of position, I can make a graph of what the potential was. It's a harmonic oscillator potential. And then if I make a graph of what the wave function looks like for a state, it's this sort of very sharply peaked thing. And that's oscillating back and forth in the potential without spreading out and without dissipating or anything like that. It just moves back and forth as if it were classical. And so that's the sense in which these coherent states are semi-classical, or as close as classical as you can possibly get in quantum mechanics. All right, so we're out of time for today. Next time I'll say a couple more things about the coherent states, and then we will be moving on to the three-dimensional harmonic oscillator as our next topic. All right, so you have homework 6 that's due today, and homework 7 is now on the course webpage. I have to go somewhere for a little bit, so I'll be able to answer questions for a few minutes after class today if you have questions on the homework. Maybe let's say 10 or 15 minutes at most. Then I have to go, and I should be back at 3 o'clock. If anybody wants to ask more questions, we can meet on Zoom, or you can send me emails as you see fit. All right, so I'll turn off the recording now and